Hey there. Today let's try to solve this problem called number of effective subsequences. So in this problem you are given an integer array nums. The string of the array is defined as the bit whiles, or for all the elements. A subsequence is considered effective if removing that subsequence strictly decreases the strength of the remaining elements. So basically when you select a subsequence and then the remaining subsequence, we do this bit while OR. If that remaining bit while OR has a strictly less value than the original bit while OR, then that subsequence is considered effective, and we just need to return a number of such effective subsequences in nums. Since the answer is maybe large, return it in modulo 10 to the power of 9 plus 7. Yeah, and let's take a look at this first example. Nums 1, 2, 3, and the answer is 3. Let's take a look why is that the case. Nums equals to 1, 2, 3, and answer equals 3. So, well, first of all, the power is like 1 or like 2 in binary. 2 is 1, 0. This 1 is 0, 1. 2 is 1, 0, and then 3 is like 1, 1. And it gives us like 0, 1, 1. Because or of this. And then in decimal, it will be like 3 in decimal. So that's why it says like the power is 3. Okay. So let's take a look at our subsequence that are effective. So let's take a look at 1, 3, 1, 3. So let me write 1 is in binary is 0, 1. 2 in binary is 1, 0. 3 in binary is 1, 1. So 1, 3 is just like 0. So the remaining is 2. So the remaining 2 will be 1, 0 in binary. So because 1, 0 is like, strictly less than this one. So this is one of the answer. And then 2, 3, we select that. The remaining is 1. And that is just 0, 1. And 0, 1 will have like basically still strictly less than that. And then also we have 1, 2, 3, where basically we select everything, and this has to be like 0. It's just 0, and 0 is obviously strictly less than 3, and so that's why we have 3. Well, let's take a look at 1, 2, for example. And then the remaining is 3, and then 3 in binary, as you can see here, is 1, 1. So here 1, 1, because 1, 1 is exactly the same as the original power. So this is not valid, so on and so forth. You get the idea. So that's why we only have 3. The answer is 2 is just 3 subsequences that are effective. Yeah, that's pretty much all for the problem description. Let's think about how can we actually solve this problem. So in order to solve this problem, usually just when we start, we just get the power. Sorry, I keep saying power, it should be strength, but you get the idea, it's similar terminology. Get the strength of nums, just basically just or bit whiles or for our element. So once we do that, for example, we will have something like, let's say the strength equals to this. Strength equals to 1, 1, 0, 1, 1, 0, 1, 0, for example. And then, well, let's think about in what situation can we actually have like, well, we have nums, for example. Nums will be something like this one. Well, let's just write it. 0, 1, 0, 0, 0. It could be something like that. I'm just writing the number in binary, so it's just easier to get the idea. This might be 0, 0, 0, 1, 1, 0, 1, 0. This will be, it might be 0, 1, 0, 0, 0, 0, 0. How many 0? So, and then 0, 0, 0, 1, 0, 0, 1, 0. Something like that, so on and so forth. We have a lot more elements, but we just take a look at the first field. So imagine like we have a string like that after doing all the bit while OR for all the elements. So let's think about how can we actually decrease value in the string. So in order to decrease the value in the string, we can have one less element. For example, we can have, like, we can turn off this one. So we don't have to turn off every bit. We just have to turn off one bit that is on in the string. We just need to turn off this bit. And then we will be able to like get a lesser string. So what I'm trying to say is that if we want to get rid of like ith bit, and then what can we do? We just need to like filter out everything in nums that have ith bit on. So for example, these nums, if I want to get rid of this bit, and then I just this will be filtered out, and this can keep, and this can keep, and this can keep. The reason behind it is that because everything remaining can form a subsequence. But no matter what, sorry, let me spell that out first. Subsequenced, everything remaining can form a subsequence. For example, here you can have more, but you can do any like subsequence. You can have like this ARN and this and this, or everything ARN, or just have these two ARN, or just have the first and the third element ARN. So basically, we can do any subsequence after filtering out. But no matter what we do, the ith bit will be off. So because the ith bit will be off, then it means that this string can never reach its full value because this particular bit is already off. Cross out that. So let's assume the remaining length is this one, is this value, and everything 2 to the power of remaining length, because we can pick any subsequence, -1, because like you can just imagine a binary number like 0, 0, 0 means we don't include everything. 0, 0, 0, 1 means we include the first one, we only include the first one, and 1, 0, 0, 1 means that we include the fourth one, and we include the first one, so on and so forth. The reason why we -1 is because we don't want to include like the empty one, because it's kind of like a special case that we don't want to consider right now. So yeah, so it's just like that. Answer plus equals to like 2 to the power of remaining length -1 that we can take care of. So any subsequence happening in here will not have the ith bit on. And then we will have another problem. What if a subsequenced string has 2 missing bits? So let's assume there's like a subsequence. That subsequence has subsequence have a strength of that, like missing 1 bit and 3rd bit. Because we have to do that, we have to iterate for every I, and because it is missing for the 1st bit and missing for the 3rd bit, and it is the same subsequence. That's why we have overcounted it. We have get rid of it more than once, but in reality, we just want to remove it once. So that's why if it has 2 missing bits, then we need to subtract it back. And the similar question comes when, what if a subsequent strength has like 3 missing bits? So if it has 3 missing bits, and then when we try to subtract the 2 missing bits, we will over subtract the 2 missing bits, basically. So that's why if it is 3 missing bits, we have to add them back. So basically, it is more like an inclusion exclusion. Exclusion. So if like the missing bit count is Mach 2, let's do it in this way, is odd, then include, else exclude. Yeah, that's pretty much all. Then we can give us a brute force solution. And to calculate the bit count is actually another topic or another technique called sum over subset. Then I think I will explain that in the next video because it's quite complicated. So let's think about how can we actually use the inclusion exclusion portion or the technique to actually solve the problem. At least just give us a time limit exceeded version. Now, so let's move on to the implementation and see how can we actually implement this inclusion exclusion principle. Try to implement the brute force solution, and then let me try to reiterate what we're gonna do here. We need to iterate or mask under the strength of nums. That's the first step. And then for each mask, we will exclude or x in nums that has turned this mask on. For example, like if the mask equals to 1, 1, 0, 1, 0, 0, and then nums equals to, for example, 1, 1, 0, 1, 1, and then maybe 1, 1, 1, 1, 1 here, and then this will be like filter out because it has turned on this mask, and then yeah, so on and so forth. So after filtering out everything, remain doc sized. I mean 2 to the power of, we need to do answer plus equals to 2 to the power of remain dot size minus 1, and then do answer to remain dot size for like, so after filtering out everything, this one for remain dot size is odd, because the first one, for example, the first one we're gonna include that, and the second one is gonna exclude that, and the third one we're gonna include that. So every time we include, it's gonna, the remain size gonna be like the bit, sorry, not the remaining size, like the bit count of mask is odd, and the bit count of mask is even, and so on and so forth. Okay, and then we will get the answer. So let's try to code that up. Let me initialize nums sized, and then we create a mock e plus 7, and then the answer equals 1 initially. This one is just removing everything in nums. It's just empty subsequence. That's why we never consider any subsequence here. We always -1. That's because it's like more like a base case. We already considered it initially. Because if you think about it, if you remove everything in the nums array, and we have nothing left, and that nothing left must have a strictly less strength, because this is an empty array. And then the total strength will be 0. In the beginning, we just calculate the total strength, nums strength or x, and then the maximum of bit is just we're going to use this built-in function in C++ to count the turn on bit. And then after we get that, we just need to know, because we need to know which mask should be added and which mask should not be added. So that's why we want to have this data structure called mask of like bit count. So that's why we need to do the max bit before. So mask of bit count B means a list of mask with bit count equals B. Okay, let me do that here. And then we need to do the modular, because we need to like make sure the answer is within 10 to the power of 9. So we need to do add. So let me just write this lambda function real quick. C equals A plus B. If C is greater or equal than mock, C minus equals mock, and return C. And subtract, similar thing. We take A and B, and C equals to A minus B. If C is negative, and then C plus equals mock, and just return C. Just return C. And we also have multiplication. Similar thing. A, B is return long. A times B mock. And then we need to do the 2 to the power, because this could potentially be quite large. That's why we want to pre-calculate the value first. And it has to be within 10 to the power of 9 too. That's why it's very beneficial for us to pre-calculate these 2 powers value. Here, 2 powers I, it just means 2 to the power of I mathematically. So 2 power 0, 2 to the power of 0 is 1. This is known. And then we're going to keep using the previous 2 power psi to calculate the next 2 power psi, basically. power sign, the current value. We can make use of the previous value, assuming it's already done. And then multiply by 2. And then we'll get all the 2 powers. And then we can iterate for every mask. Mask equals 1, mask less than or equals to strength, mask plus plus. And then we make sure this mask does not have any bit that is outside of the strength, because if it has turned any bit that is outside of the strength, it is kind of irrelevant in our calculation, because again, later we're going to use this mask to determine what we're going to exclude. But if it does not exist in the first place, there's no use for them to like include that. So what are we going to do? How do we make sure that this mask only appear the bits that appears on the strength? So we're going to do mask and strength equal mask. So if mask appearing any bit outside of strength, we won't have this. So that's why if that is true, and we can just add that to the calculation that we're going to do later, and we're going to use that built-in function from C++ again to do the bit counting, and push back mask. Okay, and then we're going to do the inclusion exclusion as we mentioned before. First step, we're going to include, so we're going to do the b count equals 1 initially, and we can go up to, you know, like the size of the b count sized b count plus plus, and then for every mask under this mask, under this bit count equals 0 for nums. So again, let me try to rephrase this. We want to exclude every x in nums when mask is on. So basically what we're trying to do here is that if we exclude every numbers in x that has turned the mask on, then we have the remaining, right? And the remaining, no matter what subsequence we do to the remaining, the mask must be missing. That's why we're going to do that. So how do we make sure that this x does not turn on this mask at all? So there's the bit operator we can do. If x and mask equals 0, this means that x does not have anything turn on for a mask at all. And then we do the count plus plus. And then after that, again, after this filtering, we know this count, no matter what subsequence we do, we cannot fulfill this mask. So let me do the current is, it should be 2 to the power of like count minus 1, because again this 1 stands for empty subsequence, which we already included in the first answer here, like initially. So that's why we can just do subtract 2 pals count and then 1. And then if now it's include, and then we're just gonna add answer car. And if it is exclude, then we're gonna do subtract instead of add answer car. And then after each bit count is done, and then we just turn inclusion to exclusion. Include. And then finally just return the answer. Let me check. That should be it. Try to submit. Um, 29. Okay, there's a missing semicolon. Start again. Okay, so missing semicolon again. Okay. Okay. The sample test case seems fine. Let's try to run that. Again, this won't get us accepted because we are still very slow. But let's see if it can give us at least a TLE response. Okay, we passed a lot of test case, and then our code failed on the time limit exceeded. And so basically, the bottleneck is just the calculation here. We're gonna do that like repeatedly for a lot of times. So there's actually another technique that we can improve this, which is called sum over subset. And then once we do that, we're gonna improve the time complexity. So right now the time complexity is let me think. So this one is, so this is just iterating everything here. You can assume this is ON. Bit count, this is like the strength. So this is, so everything here should be, at this point it should be O like nums I. And then when we do here, this one is like O nums I times n basically. N is the length of the nums. So yeah, that's why this part will actually give us timeout. So let's think about how can we improve the time complexity for this part. So what is sum over subset, also known as SOS, that I mentioned like repeatedly in the last few minutes? So now we know that we want to find this x and invert mask equal x. So this invert is also just a binary. So what we want to do basically is like this. Let's say that this est mask will contain the number of elements x in nums such that mask and x equal x. Right? This is exactly what we are looking for. And then we have a recursion mask I. So this represents number of elements x in nums, where mask x and x equals to x, and we only allow first I bit to vary. So what I mean mathematically is like this: mask and x equal x, and mask, because we ignore the first I bit, the first I bit can vary, but the last the remaining part must be equal. So it's like this. So the remaining should be exactly equal, I plus 1. So this is what we look for, and we need to like return to count how many x in nums will fulfill this. You can do something like this in Python, I guess. So basically it's like this. This is what we're looking for. So now, because of this like definition, we know the base case will be like this. So what is -1? -1 means we do not allow any variation. So what does that mean? Because it's -1, we can see the definition is that the first ith bit can vary. So right now it's like we start from 0, and -1 is just basically means that everything does not have any variation. So we just need to know the frequency of mask. And for ask mask I, how can we do the recursion once we know the base case? Okay, so when 2 to the power of I is off, then first of all, in order to fulfill this mask and x equals to x condition, all x ith bit must be off. See, because if the current bit that we're looking for is 0, like in terms of the mask, right? The mask ith bit is 0, and we need to fulfill this condition: x mask and x equals to x. So if x happen to have some value in this bit, and the final end will be missing. So the final end will not be x, mask and x will not be equal to x, will be less than x, right? Because we know mask I is, the ith bit of mask is 0. So that's why the x has to be 0 here. So that's why we do not have any option for us. And then that's why so there is no room for changing. We can only pick 0 on this bit for x, basically. So the final answer for that is just mask and then I minus 1, and then we do that recursively. And next, when the current bit is on, Okay, maybe let me. So this A, and then this is the conclusion B. So let me do it here. It's on. So what does it mean? If it is on, then it means that well, obviously we still need to fulfill the X mask and X has to be equal to X condition. But this time we know that this is on, right? Because this ith bit of mask is on. So it doesn't matter this X ith bit is on or off. It can be on or it can be off. It doesn't matter. No matter what we choose, this, well, obviously we might have a situation that the X ith bit is off, but the mask ith bit is on, right? If that's the case, then we just don't turn on this bit, and this still wouldn't violate this condition. And obviously, in the other case is when the mask is on and the X bit is on, then still it just means that we won't lose anything by turning it to 1 or 0. So that's why we can just turn it as 1 or just treat it as 0. So basically, what I'm trying to say is that the answer can be ask mask I minus 1. Or we have to ask mask XOR 2 I minus 1. So what we're doing here is basically just treat the mask, well, because right now we know that the ith bit is on. What we're trying to do here is to basically turn off this bit, because this restriction is not necessary. We just assume that it does not exist, because finally when we reach -1, we're going to ask this mask, right? If we just turn off this bit, it means that, okay, this mask is not a restriction. It does not have to appear. So that's why it's kind of like, you can think of it like we're leaving the restrictions, so to speak. Okay, so we know when ith bit is on, off, then we just do as mask -1, and if the ith bit is on, we do the mask I minus 1. This is when we treat the ith bit as 1, and this is for treating the ith bit as 0. And then ask mask max bit. This is max bit. This max bit, it can be 31 or it can be 32. Basically, it's just the maximum bit that is large enough to cover all elements. So, well, we can do some left shift. Like we still remember the strength is the total OR of like this whole array. Then we're just going to get the left, like maybe just do this. X equals leftmost bit position of this one. You can imagine something like that, maybe +1 to give us some room, but you get the idea. So this max bit is never going to be like related to n. It's just, so it's just a constant number. That's what I'm trying to say. So this is the max number. So this will be another like base case. It's not base case. It's like the first case that we look at. So this, well, we plug max bit to I. So let us read this again. So we basically that, right? Because we only allow first ith bit by I is like the max the max bit. So basically just ignoring the second restriction. Because the first like 32 bit, it just means every bit can be variable. So the only restriction now is this. So this is exactly what we look for as well. This is exactly what we look for. So this is also the answer that we're looking for. And also equals to S mask. So once we have this like DP, and we can go back here, and instead of doing this whole for loop, let me just create that. We can just do like something like this. Count equals to this one, mask. And we can get rid of this. And the whole thing is going to be so much faster because we don't have to iterate this loop over and over again. And obviously, we're going to do some memoization DP on this one. Yeah, but that's the general idea. Let's see how can we actually implement the whole recursion stuff. So let us copy this count to the original implementation here. And then we can comment our previous stuff here. Again, because we are originally doing that, if we want to change this condition to, let's say here, we need to do the inverse mask. So here, the more accurate representation is with the invert. The invert just means like flipping every bit. So I'm going to write this helper method first for inverting like every bit. Basically just turn 1 to 0 and 0 to 1. Okay. So let me go to here. Auto invert goes to this one. Next, and then result is 0. And then for I 0, I less than max bit, I plus plus, if x and 1 I equals 0. If it is 0, then we just flip it to 1, basically. If it is 1, else it is 1, then we just ignore it. Just keep it as 0. Finally, just return result. So this max bit, originally we are using the number of bit in a string. Now it doesn't work anymore because it's kind of like you need to loop through all the position instead of getting the count. So the max bit, we're going to change that to the leftmost bit of string, and the leftmost bit is also helper method. Most bit x. So this just turn the leftmost position, the most significant bit that is turned on in x. First 1, result is 0, while x is greater than 0. And if x, the current bit is turned on, and then maybe we can just remove this extra parenthesis, just here, post, and just right shift 1, and then post plus plus. And finally, we just return rest. Okay. This will give us the most significant bit position, and we're going to use that to decide how much we're going to invert, because we don't want to invert anything because it's just a waste of space for the most part. Now we have this invert let me scroll back down here. So this count, now we have this invert, we have this max bit. Let me change to lowercase here. This as is this as is just calculating the number of elements in X such that it fulfill this condition. Let me just write the helper function maybe here. This gives us the function header. So it will return an integer, and it will receive two parameters. The first one is the mask, the second one is I. Asked, and asked will be, well, it will have access to every address in the current function as well, including the nums array, so I don't have to pass that to the parameter. So the first is mask, the second is I, and then if I equals to -1, we just return free mask. So this frequent is another like data structure that I haven't included yet, but it's very straightforward. Maybe I can create it now. This is just the frequency of each number that appear on the nums array. So this one is 3. Let's make the dimension as max bit, and one left shift max bit. So basically it should cover every number. So it probably won't go over. It won't go over the limit. So ext nums frequent x plus plus. So but as you know, we inferred it. So it is possible that this mask can go over the original like value. So just to make sure that it won't go over the index bound, we just add a little check here. If mask is greater or equal to 3, sized, and then we just return 0. Otherwise, we return the frequency, and then we can finally start calculating the answer. So first, if the current I bit of mask is on, then as we mentioned before, there are two options for us. We can either treat the current bit as 0 or 1, because either way, the final x can be 0 or 1, because mask has turned on anyway. It won't make a difference. It won't make a difference in terms of fulfilling the condition of like x and mask equals to x. So this one, let me here. So this is just basically, treating, well, finding x as 1 on this bit. So we just move the position 1 to the left. And this is treating it as 0. So this is just turning off the mask bit. And then this is the else case. This is when the ith bit of mask is currently off. So if it is off, then the final x has no choice but to be off as well. Because let's think about it. If the mask bit is off, but the x bit, the x ith bit is on for some reason, then there's no way that mask and x finally will be x, right? Because no matter what, this current bit will be missing. So that's why if the mask ith bit is off, then ith bit must be off as well. So that's why we have less choice if the mask bit is off for the ith position. So we just minus 1 here, and finally we just return answer. So, well, that should be it. Obviously, this is still very slow. Actually, it's even slower than before because this is exponential, because we haven't done any memoization step yet. But you can see it's like a very clear DP stuff that you can optimize. Let's see if it works first. Leftmost bit, line 17. Okay, I should put this. After the function declaration. Okay, so as you can see, like, this is kind of giving us the correct result, but if I submit, it will definitely go way above the time limit. So let's think about, okay, this is lagging right now. I probably shouldn't have clicked that, but you get the idea. So, but yeah, you can see it passes all the wrong answer test case, I assume, because we have passed 900 test case at this point. So the only issue right now is the time limit exceeded. So it also shows that the formula we have there, we have here, is actually correct. So the next step will be just trying to optimize it using DP. Let's try to optimize this function, this recursive function, using DP. So let's do iterative DP. We know that we're gonna loop for, like, first is to I, and we also know we're gonna loop for a mask, but we don't know the order yet. But we know that we have 2 parameters, so that's why we have 2 nested for loop, and we just directly copy the function header here. Let me copy the function header. Let me go to here. So if it is -1, then we just do like this, DP, mask, and then I. Equals to this one. And otherwise, is this one, and then we just continue, because this is the return, to just simulate the return here. Otherwise, if the current bit is turned on, then previously we do this recursive call. Let's change this to DP. And this one is same as well, change it to DP. And this one, same as well. So DP mask answer. So that should be exactly the same. But if you noticed, if you look at it carefully, you can see that it's always looking at I minus 1. So in DP like that, it means that we don't actually need to, create or like max bit of mask. We just need to create 2. So in our case, we can just create 1 because of, like, if we iterate the mask from like, let's say 0 to the max bit, then we can just get away with like creating a lot of like DP array here. So what I'm trying to say is that we can just get rid of this I minus 1 because, because when you access this, we just assume that it is already, because this one is going to be smaller, right? This mask, this is basically turning off the mask. So we just need to make sure when we iterate the mask, is going from, let's say, the smaller to the biggest. So dp sized and then mask plus plus. And this one is the same as well. We don't need to do the I, we just need one DP dimension here just to save space. And again, we're going to, well, the minimum is -1, so we're going to start from -1 and then all up to the max bit. So yeah, that's pretty much all. Let me try to create the DP array here. So again, the dimension you just need to make sure that the mask will never go over it. So one left shift mask bit time should be safe enough for us to do that. And then finally, we don't need to call the as function here anymore. We just need to do the count dp invert of this mask, which just give us the exact same result as before. That should be it. Let me try to run code again. Max bit. Okay, using a semicolon here. Okay, and seems to work. Let's try to submit. So, and then we finally got accepted for this problem. And finally, just let me quickly do the complexity analysis. So this one, we are going through the most time-consuming part is obviously to fill in this DP array. And then this is basically, so it's the num sign, and then we also have this max bit. This max bit is basically, in the worst case scenario, it will just be the number of bits in nums. So we can just assume that is the log num I. And then we also need to iterate every mask here. So it's just nums I times, well, maybe just nums I log nums I. Where nums I, you can assume, is probably the maximum of that or the total or of that. maybe just x log x, where x is the strength. Yeah, that should be the final time complexity. This is the time. Space, it will be something, because we just have this here, and then it will be just OX. Yeah, and that's pretty much all. I know it's like a very complicated problem, and but I hope you at least like get the general idea of the solution. And yeah, that's pretty much all for it today, and I will see you next time. Bye.